In this video, we're going to discuss rules of logarithms. Rules of logarithms. And so there are several rules. Some of these rules kind of come from properties that we already know, but in the examples that I'm going to use, if I use a capital M or a capital N or the letter A, they're all going to be values that we're going to assume that are greater than 0. And so the first rule, the first two rules actually are what we call our inverse rules. And so notice here, I have the log at base A of A to the X, right? The reason why we call this the inverse rule, because this is actually a composition of functions, right? Say that f of X was log at base A of X and G of X was A to the X, then this example here will be f of G of X, right? And remember that the log at base A of X and A to the X are inverses of each other. And so when we studied inverse functions, we found that if I do a composition of inverse functions, they're always going to equal your input value, which is X. So log at base A of A to the X is just X. We can do the inverse property the other way around. So if I use the same F and G here I have A to the log at base A of X. That is a little too thick now that I wrote that down. This A to the log at base A of X is actually G of f of X. And we have the property that when we do a composition of inverse functions, it takes us back to our original input. So that just equals X. So A to the log at base A of X is X. And so when I look at this, notice here I have the common log, right? There's understood to be a base 10 there, log at base 10 of 10 to the y plus 1. Well, that just equals what your exponent is on your 10 and your argument there, your input. So that just equals y plus 1. And then here I have e to the ln. Notice e and ln are inverses of each other because the natural log is the log at base e. They cancel each other out, or they undo each other because they're inverses of each other. And so this is just going to equal the square root of y. We have the product and the quotient rules. The product rule says that, hey, if I have log at base A of m times n, so these are two positive numbers, then what we can do is we can separate this or expand it so that we can do the log at base A of m plus log at base A of n. It's almost like the product rule when you have exponents, right? When I have a product of two exponents, then how do I simplify the exponents? I add them together. All right, this is how it looks for logarithmic functions. And so we could write the natural log of 4xy in expanded form because that 4 and that x and that y are all multiplied by each other. And so I can write this in expanded form by doing the natural log of 4 plus the natural log of x plus the natural log of y. All right, and that's a plus sign right there. We have a similar rule with the quotient rule. All right, now remember when we had two bases that were the same and we divided them, then we simplified that by doing the subtraction of the exponent, That's our quotient rule for exponents. We have a quotient rule for logarithms that is similar. I can rewrite this as the log at base A of m minus the log at base A of n. And so in this example here, I have log at base 3 of x plus 1 all over x. This in expanded form is going to be log at base 3 of x plus 1 minus the log at base 3 of x. And then the last rule is our power rule, right? We have a power rule when we look at exponents. We usually call it a power to a power or something like that. But when I have a power to a power, we actually multiply the exponents. That's m times n. And so since a logarithm itself always equals an exponent, then what we can do when we have log at base A of m to some power p, and that p can be any real number besides 0, of course, because then that would be m to the 0 power, which is 1. Then what we can do is we can bring this power p to the front and multiply it in our logarithmic statement. So that would be p times the log at base A of m, all right? So we'll bring that power out front and multiply it. This sort of comes, if you think about if p is a whole number, from the product rule here. For instance, if I had log at base A of x cubed, what x cubed is log at base a of x times x times x. And if I were to use my product rule, which we have here, which says that if I have a product of two things in my input of my logarithm, I can write it as the sum of the logarithms. So that's the log at base a of x plus the log at base a of x plus the log at base a of x, base a of x. And when I add something three times, that's three times the log at base a of x. It doesn't only work for integer exponents or whole number exponents. It works for any exponent. You can bring that p out front and multiply it in your logarithm. Right? And so we can write this logarithmic expression here in expanded form. First, that's a 3 times the square root of x. So I can write that as log, the common log of 3, plus the common log of the square root of x. And notice the square root of x is the same thing as x to the 1/2 power. So that'll be a log of x to the 1/2 power. And if I wanted to further expand this, I could use that power rule by bringing that 1/2 out front and multiplying it. So that'll be a log of 3 plus 1/2 the log, the common log of x. All right. So that again, let me make sure that you can see that, plus 1/2 times the common log of x. All right. So that's using that power rule. And so you want to get good at going back and forth using these rules here so that you can express your logarithmic expressions as a single logarithm, and then we're going to be able to expand also. And so let's look at this example here. It says rewrite each expression as a single logarithm. I have the natural log of x plus 5 times the natural log of x, right? Okay, there are a couple ways that we can do this, all right? What I'm going to do is I am going to, well, you can notice that these two, let's just focus on using the logarithmic rules, right? Before I start combining these things, I'm going to make sure that I have the same base on my logarithms, which I do have my same bases. I'm also going to make sure that I have the same a 1 in front of all my x squares, in front of my logarithms, all right? And so since this one has a 5 in front of it, what I'm going to do is I'm going to use my power rule backwards, and I'm going to write that as the natural log of x to the 5th power. Okay, that's the power rule backwards, right? The power rule says that if I have the log at base a of m to the p, I can bring that p, write that as p times the log of base a of m. So I'm starting on this side here, and I'm rewriting it in this form here. I'm putting that 5 as the exponent on that x. Now that I have that, I have this plus sign, and if I want to reduce that into a single logarithm, then I can write that as x times x to the 5th as our input into our logarithmic expression. And so this will be the natural log of x to the 6th power. All right, now this is 1 natural log of x plus 5 natural log of x. So that's 6 natural logs of x's. So I was going to do this example like this, and then I can use my power rule to write that as the natural log of x to the 6th. That's probably a quicker way to do it. But in general, we want to get a 1 in front of our natural log statements, or a negative one, because sometimes we'll subtract and use the quotient rule. And so what I always like to do is go this method. If I'm going to write, my goal is to write it as a single logarithm. But you could have done this one this way here too. Let's go to part B here, where I have this long expression here. Notice here, all of my logarithms are at base 2. All of them are at base 2. So what I'm going to do first is I'm going to get my coefficients on my logarithmic statements to be 1. That means I'm going to use my power rule first. So I'm going to do log at base 2 of x to the 5/6 plus log at base 2 of y to the 2/3 minus log at base 2 of x to the 1/2 minus log at base 2 of y. Now, I want to simplify this until I get to one single logarithm, because all of our logarithms are at base 2, the same base. Notice here that both of these are positive and both of these are negative. In fact, what I'm going to do here, and you don't necessarily have to do this, but since these are added together, I'm going to go ahead and write them as a product. That'll be x to the 5/6 times y to the 2/3. But what I could do here is, since both of these are negative, then what I could do is I could factor out a negative here. and then these become positive. The second term, or both of these, become positive. Now I can write these as a product as well. So that would be log at base 2 of x to the 5/6 y to the 2/3 minus a single log expression, but both of these are going to be multiplied in the argument or the input of our logarithm now. And now that I have a single subtraction, I can use my quotient rule and I can write one single logarithm. My numerator is going to be x to the 5/6 y to the 2/3 divided by x to the 1/2 y. And now this just becomes a simplification of things like that we did at the very beginning of our course. Since my bases are the same, I can subtract my exponents. 5/6 minus 3/6 is x to the 2/6. And since this is a 1, I'm going to subtract the 2/3 from 1 and put this in the denominator. That's going to be y to the 1/3. And so I can write this as log at base 2 of x to the 1/3 over y to the 1/3. And if you didn't want to write that 1/3 as a single, as two separate powers, you can simplify that further, x over y to the 1/3. And if you wanted to write it as a cube root, you definitely could. All right. And so we wrote it as a single logarithmic expression and we simplified it completely. All right, so we've gone from having logarithms written in expanded form. Now we want to go and write from expanded form to be written as a single logarithm. Now we want to go from a single logarithm and write it in expanded form. And I'm realizing right here that I definitely don't have enough space. So I'm going to make some adjustments to this. Hang in there for me. All right. So let's look at this example here. We're going to go from having this single logarithm to having it as a sum of multiple logarithmic expressions. And so here, the natural log of 5 to the negative x over 2. If I want to expand that, I'm going to write this as the natural log of 5 to the negative x minus the natural log of 2. I can further expand this by bringing this negative x out front using that power rule. And I have this logarithm in a completely expanded form. Let's go to part B. We have log at base 4 of 3x square root of y over the cube root of x minus 1. If I'm going to expand this, I can write this as log at base 4 of that numerator, which is 3x square root of y, minus the log at base 4 of the cube root of x minus 1. Right? Now, there's still some expansion that I can do because that's a product of three things. So if I want to expand this completely to where there's no powers and no multiplication or division inside of my input of my logarithmic statement, then what I'm going to do is I'm going to write this as log at base 4 of 3 plus log at base 4 of x plus log at base 4 of the square root of y. And the second one here, that's just minus the log at base 4 of the cube root of x minus 1. Now, this log at base 4 of 3 can't be simplified any further. You can't expand that any further. This one right here can't be expanded any further, but these two can. And whenever we see a radical, remember that is a fractional exponent. And with those fractional exponents, we can use our power rule to bring that exponent out front to be a product in front of our logarithm. So if I want to simplify this, y to the square root of y is y to the 1/2 power. So we can write that 1/2 out front multiplied by a logarithmic statement. And the cube root is your exponent 1/3. So I can write that as minus 1/3 log at base 4 of x minus 1. Now, we rarely want to write our logarithmic expressions like this. Okay? Most of the times we want to go from having logarithmic expressions written this way to the condensed form. It'll help us when we start to solving some logarithmic equations, which we'll see later. So we're going to be more likely to look at examples that may look like this and trying to end up with an example or an expression that looks like that. All right, but we want you to be able to go both ways so that you can get used to this process of expanding or reducing logarithms into certain expressions. Some other useful rules here for simplifying logarithms that may come up later, or that may be something that you see that you can quickly simplify. Log at base a of a, remember these are inverse functions, and so this is going to equal the exponent here, which is understood to be a 1. So that equals 1. Log at base a of 1, this means what power do I raise a to in order to get an output of 1? That's going to be 0. The ln of e, remember they're inverses of each other, and so if you think about the inverse rules that we went over, it's going to equal the power here, and that power here is understood to be 1, and so that's 1. The ln of 1, well, this is the power that you have to raise e to, which is your understood base there, in order to get 1 as your output. It's going to be 0. My line here is missing. The common log of 10, remember that's a base 10 there. What power do you raise 10 to get 10? That is 1. And then the common log of 1, what power do you raise 10 to get 1? That's going to be 0. Okay? Let's look at this last example, and this video is turning out to be quite quick. It says one of the cheapest new cars you could buy in 1970 was the Ford Maverick at $1,995. In 2009, the cheapest new car was probably the Kia Rio, which is $10,890. Use the formula for compound interest to find the annual growth rate to the nearest 10th of a percent for the price of the cheapest new car, right? And so remember, when we see that formula, all right, or when we see compound interest, the annual growth rate, we don't see anything about continuous, so I'm going to use that formula A equals P times 1 plus R over N to the NT. All right, and so my P naught is 1995. I don't know this R here, so that's what I'm trying to find. And the prices are going to change once a year, right? So I'm going to put an N equals 1 here. And 1970 to 2009 is 39 years. And in 39 years, the cheapest new car was $10,890, right? And so I get 10,890 equals 1995, 1 plus R to the 39th power. All right, this is just an example. And here I'm going to have 1995. And that'll give me a 1 plus R to the 39th power. And so I take the 39th root, and I'll have my interest rate here, or 1 plus my interest rate. Which means my interest rate is this number minus 1. And so I'm going to show you how you can put that in your calculator. Remember, when you raise something to the 39th power, if you have a graphing calculator, it'll do that for you. Let's see here. So if I cut my calculator on, I'm going to have, okay, I got to do the 39th power. So I'm going to put the number 39. I'm going to go to math. Option 5 allows me to do other roots besides the square root and cube root, which is popular, right? So I'm going to go to option 5. And notice how my calculator put my 39 in the root, the index place, right? If your calculator doesn't do that, it may have that X with the root in there. That's perfectly fine. All right, I'm going to put the 1,890 in my calculator, divided by that 1995. I press enter, I get that, and I'm going to subtract 1 there, and that's 0.0445, and I want it, so let me go ahead and put that in my on my paper before I forget. R is approximately 0.0445. Let me make sure I did that right. 0.045, yes. And so what we want to do is we want to round that to the nearest 10th of a percent. And so remember, when you change the decimal to a percent, you multiply by 100. So that's approximately 4. Let me put that 447, whatever in there, right? So if I move it 2 places to the right, this 4 would be a 4. Would not round this up to a 4 here. So I'm going to say that's 4.4%. All right. Now, this said nothing about continuously, right? But if I were to assume, we're going to redo this exact same problem, and we're going to assume that the price of the car is changing continuously, right? If that were the case, then what we would do, PE to the RT. All right, and I will use the word continuously so that you'll know to use that formula. Usually with financial things, you have the option, more natural things changing this way here. But if I were to use this formula, I would do 1995 as my initial value. I don't know my rate, but I know 39 years later, I'm going to end up with a car that's $10,890. That's the cheapest value, right? I can divide both sides by 1995. Oops. And I get that 10,890 over 1995 equals e to the 39r. Now, this is where we're going to need our logarithmic function, right? So what I'm going to do is, I know that we can change this to logarithmic form because we've done this example where we change an exponential equation to logarithmic form. Notice I can't do the same method I use over here because I don't have a constant as my power. My power involves my variable. And so the logarithm, since it is the inverse of your exponential function, what we can do is we can do the natural log of both sides, because I know that this side right here is positive, so the natural log exists, and e to any power is always going to be a positive number, so this is positive. When both sides of your equation are positive and you want to solve for your variable, which is in an exponent, you can always take the natural log of both sides. So I'm going to take the natural log of both sides. Let's make sure that you can see this in our on our screen. We can. And what we're going to notice here is two things. My left-hand side is going to stay the same here. But my right-hand side, now we could use our power rule to bring that 39r to the front, or we can realize that we have inverse functions here. And so the natural log of e to a power, the natural log and e, they undo each other. And so I'm left with just 39r. We can divide both sides by 39. And then we can put that value in our calculator, and we'll have an estimate of our actual rate. And so natural log of 10,890 divided by 1995, right? That's on the input of our logarithm. We divide that by 39, and we get 0.0435. Okay, I wish I could just I'm just going to take a picture of this. All right, I'm putting this on my paper. All right. And so if I round that to 2 decimal places, right? I get the percentage, so that's 1, 2, and round that to 1 decimal place because it's the nearest tenth of a percent. That's going to be 4.4%. Now, these values won't always be the same, right? They're actually not the same, but within rounding, they are the same. But this one requires us to use our logarithmic properties, our properties, our rules of logarithms. This one did not. I wanted you to see both of these. Since this one didn't say annual, then we technically should use this one here. But since this one did not, I wanted you to redo this problem with your logarithm. And so this example, we assume that it changed continuously. And so when I assume that it changes continuously, I ended up with the same rate. All right, I will be clear in class when I want you to use this formula versus this formula. But this is it for this video. I'm sure you hear that alarm. I'm sorry about that. But that concludes this video. See you next time.